Today's talk was a bit more introductory, so I apologize that today is going to be, I'll have to ramp up a bit and it's going to be somewhat technical. Otherwise, I will never get to the interesting stuff. But I will try to sort of define everything that as I go along. There are certain things like D-branes, I don't know, I cannot possibly explain, but so I will try to avoid things which probably you do not know, all of you. So the first part will be actually almost purely mathematical. So it's like you can think of it as a, so yesterday I explained everything about quantum black holes. And I sort of explained the connection between this and modular forms. Now I will try to explain what are modular forms in a complete generality. And then in the end I will sort of tell you how once again the two get connected. Okay, so the first part is going to be really like mathematics, purely mathematics. And I thought this, because in some ways, mathematics is easier because you can give definitions and then you can state a theorem. Whereas if I have to explain what is a D-brane, it's a long story. So I'm just going to start where it is simple, So first of all, modular forms, okay? And I think some of these techniques are of broad use. So even if you don't work in holography, black holes, or string theory, or anything like that, even if you work in condensed matter physics or in statistical mechanics, some of these results will be useful to you. And maybe I will motivate it in a way a bit later. So basically, yesterday I defined it, let H be the upper half plane in the complex plane, upper half complex plane. In the tau, with imaginary tau being equal to positive. And then there is an SL to Z matrices. Basically integer matrices such that the determinant is 1. Then a modular form of weight k as I had defined yesterday, it's a holomorphic function on the upper half plane, so it has no poles or anything like that. Holomorphic in H. Which has, as I said, it's a very symmetric function, that it has this very nice property that, and that's the reason for its importance in mathematics. So, it's like an analog of a sphere. A sphere is very symmetric. It's a geometric object which is very symmetric. And so spheres and geometric objects which are symmetric are important in geometry in a similar way. And this function, so first of all, because one of these things is, that this group is generated by two elements, tau, t is equal to tau going to t, tau plus 1, and s which is tau going to minus 1 upon tau. So any such matrix can be generated by a repeated action of, so here under this tau goes to a tau plus b. So all such transformations can be generated by appropriate combinations of these two things. Now, starting from this is basically translational symmetry, right? It's a periodic function in tau. So therefore that immediately tells you that you can do Fourier expansion, right? So this implies that f of tau, you can write it as an q to the n, where q is equal to e to the 2 pi I tau. Simply because tau going to tau plus 1 is the symmetry. Now this function as im tau, there are a couple of definitions I will give you. As im tau going to going to infinity, which is q going to 0. So if you remember yesterday in this partition problem, we have to take q going to 0 and all these limits, right? So basically if imaginary tau going to infinity is a kind of a special point, that's called a cusp. This is kind of called a cusp. So in this expansion, so this n can go from minus infinity to infinity in general. And if a of 0 is 0, sorry. Yeah. So it is, and it has to be bounded. Yeah. So generically, just by Fourier expansion, it can go from minus infinity to infinity. But if it does not have, if it is, so it can, well, it can have a pole at infinity. So it's a cusp form. Yes. So that's what I'm going to come to. So if a0 is equal to 0, then it's called a cusp form. And then the function goes to 0 as q goes to 0. Then, okay, so actually let me put it like that. If, I mean, we can now weaken the, so if you just say that it really starts at q, then it's called a cusp form. So cusp form means that a0, an is equal to 0 for, let me put it like that, an is equal to 0 for n less than or equal to 0. Then it's a cusp form. But you can relax this and you can say that an is equal to 0 for n less than or equal to minus n. And then it's a weakly holomorphic modular form. Just a definition. No, it just means that if you do the q expansion, it can have some term like 1 upon q plus dot dot dot. Q to the power n plus 1 upon q plus q. For example, the function of Ramanujan that we encountered, the partition function, right, was 1 upon q product 1 minus q to the n product over n q. If you expand it at small q, it goes as 1 upon q to the power 24, right? Plus 24 plus something times q plus dot dot dot. So this is not a cusp form. Why? Because at q, as q goes to 0, it has a pole in q going to 0. So it's a weakly holomorphic modular form. And what is an example of a cusp form? So let me give you example. Cusp form example is this function. If you don't take, this is called delta of q. Why is this a cusp form? Because look, in this expansion it starts at q. So it's completely well defined. And this is actually a very famous function in number theory. This is the Ramanujan, Jacobi Ramanujan function. And Ramanujan discovered all kinds of amazing properties of the Fourier coefficients of this guy, the tau. This is called the Ramanujan function. Now, I'm giving this technical definition for a reason, because the behavior at q going to 0 determines how fast an grows as a function of n. So that's the main reason why I'm giving this technical definitions. So cusp form, for example, has a property that its Fourier coefficients grow very slowly. And that's the kind of things that mathematicians really like. I mean, so a lot of the work, if you look at it, really, lot of the work in mathematics sort of deals in the world of the cusp forms because it has nice whereas in physics, in black hole physics, you're interested in exactly the opposite thing because you want weakly holomorphic. So cusp form means slow, almost polynomial growth. Whereas weakly holomorphic means exponential growth. So if you remember yesterday, I had defined the Fourier coefficients of this to be Pn. Right? And Pn grew exponentially. The Cardy formula, as I had explained it yesterday. So that growth is exactly related to the fact that the entropy of a black hole is finite. Since that is related to entropy of black hole, if entropy of a black hole is finite, then the number of states is the exponential of the entropy. So therefore the number of states should grow exponentially. So generically in a physics problem, you expect, related to black holes, you expect not to encounter cusp forms, but to encounter weakly holomorphic forms.
So if you didn't have this zoom picture, model invariance of objects.
Yes.
If you have a generic black hole, do you expect such objects to, such modular objects to?
No. So I will come back to that why do modular forms appear so are so abundant in string theory and what is the reason for it? And the reason for it, physical reason in one line is that basically conformal field theories are abundant and conformal field theory implies modular symmetry.
More than
Yes.
If it is infinitely differentiable, is it weakly holomorphic?
In the finite H plane it is. In the finite H plane. So this is only when imaginary tau goes to infinity.
No, suppose I say it is only infinitely differentiable. Will it be weakly holomorphic?
It could be weakly holomorphic, it could be infinitely differentiable in the finite plane, but not infinitely differentiable at q equal to 0.
But here it is infinitely differentiable.
No, it's not, because weakly holomorphic means it has poles, right? So poles means it is not infinitely differentiable.
This is less strong than infinitely.
Exactly. Cusp forms are like that, they are infinitely differentiable, but weakly holomorphic is not.
This is neither holomorphic nor infinite.
No, it is holomorphic here. There are no poles there is no term like q minus 3 or tau minus 3. There is no such term. 3i, there is no such term. But there is no, it can, at infinity, it can have different behaviors.
Is there any limit on how fast E of n can grow?
Yeah, so this is actually a huge, I can give you, people have, proving this, how fast they grow is like is an industry, it's a big.
But is there any, like for example, can go?
Yeah, so I will give you.
No, see, the reason I am asking, is it, does the Poincare lemma hold at infinity?
What does Poincare lemma has to do with this?
Poincare lemma, that means
No, but it's not relevant here.
derivative, we can actually derivative to 0.
No, but it's not relevant here. So it's not relevant here. Okay, so okay, and sorry, I said something wrong here. No, sorry. Okay, good. And holomorphic. So cusp form means A naught equal to 0, right? And everything is positive. So this cusp form starts like q plus q square plus something. Weakly holomorphic starts maybe with q to the power n plus something. Whereas holomorphic starts with maybe A naught plus q square.
The cusp form.
Yes.
It's necessary that E of 0 should be 0.
Yes, that's the definition of a cusp form.
I see. So if I take it as 1, is that a serious problem?
So yeah, so that's a holomorphic. That is holomorphic but not cusp. It's not a problem. It's just a special class. So another way to say that is that if I denote the space of modular forms with weight k, cusp forms at sk, and this as mk, and this is mk factorial, and this is a notation in mathematics, then all that we are saying is that sk is a subset of mk is a subset of mk factorial. And correspondingly here, you can show that an grows as order n to the k by 2 as n goes to infinity. K is the weight of the modular form. Here it goes as n to the k minus 1. So that answers your question. N to the power k minus 1. So you can see that this grows slower than this. And as k becomes large, this grows much slower than this.
Oh, I thought n power k minus 1 is larger than
K by 2.
Right.
N to the power k by 2.
Okay, fine.
And here it grows exponentially.
Smallest value of k is 4.
Yeah, and k large. And here it goes as what we want, c square root of n.
Well, I wanted, suppose like exponential n is, can it have, this is exponential root n,
Yes.
but
No.
why is it?
It's a proof. Right, yes. So,
For the Mach modular form also like the growth is limited like this.
okay, Mach modular forms is a separate story. Let's come to that in a moment. But the main point that I want you to understand is that it's a very simple definition of modular forms. It's a highly symmetric function. Basically, it remains invariant under SL to Z transformation, but it gets transformed with a weight k. And then you can do its Q expansion because it's a Fourier series. Because it's periodic in tau, you can do a Fourier expansion. It is holomorphic in the finite upper half plane, but it can have poles at Q equal to 0. And whether or not how its behavior at the cusp determines how fast it grows. And yes.
The deeply holomorphic, so the capital N, it appears only in the coefficient C, is it?
Capital, yes. C times, C is some constant.
Yeah, but in the definition you had 1 over q power n as a leading term.
No, this n is not this n.
That's right. But
Yeah.
will that n appear anywhere? Will that capital N appear?
I don't know generally what is this term.
Nightly it should because
Probably appear as a...
you take its nth power, I would say, my guess it will be some.
Yeah, if you do some kind of a Cardi formula,
Right.
there will be an n appearing.
The coefficient C will...
Yeah, you can depend on it. C is independent.
Probably linear.
Yeah, you can. This you can.
It came inside the scope.
Yeah, it's a fairly simple exercise from what I had done yesterday, that you just do a modular transformation and do a saddle point evaluation, like to derive Cardi formula. And then you will find out how it depends on it. Okay, now I can sort of now explain to you the sort of part of Ramanujan's magic. I mean, the part of Ramanujan's magic was that he had very good feeling for how the things are growing and how the function behaves at cusps. So from that, he had you could figure out that whether something is looking like a modular form or not. I mean, so a lot of his intuition came from looking at the behavior of that function at the cusps and see how it behaves, how it grows, things like that. And there is a second piece of the kind of the magic of modular forms, and this is something that my collaborators sort of, Don Zagier, taught me, is that the modular forms are finitely generated. Yeah.
This behavior, this conformal form where A was unknown. Is it easy to see or is it analysis?
Huh?
That AN growing polynomial, is it easy to see or is it requires quite a bit of...
No, these results are, I think, more complicated to prove than this.
So they're not applicable at all to see.
I don't know. I mean, I don't know how they are proven, so I don't want to. I mean, yeah. To get these precise numbers, I'm not sure how. Maybe it is easy, but I don't know. I mean, it's not. The thing is that we are in physics. You don't actually are interested in this and not in this. Now there are two very well-known examples of modular forms. So one of the magic is that modular forms, the ring of, so let me make the statement, ring of modular forms is finitely generated. Okay, it sounds like a kind of a technical statement, but let me just explain. So what do you mean by ring? Ring means you can multiply, right? Ring means like ring of operators. Operators you can multiply, matrices you can multiply. Similarly, functions you can multiply. And if you multiply two modular forms, their weights just add up. So if you take a modular form of weight k1, multiply that with a modular form of weight k2, it's easy to check that the resulting thing will be a modular form of weight k1 plus k2. So therefore it forms a ring in this sense. And it is finitely generated means there are two modular forms, well-known modular forms E4 and E6. That any modular form can be constructed by appropriate powers of E4 and E6 such that the weight is equal to that weight. Okay, and I can write down an explicit expression, but that's not important, or maybe I should write it. For example, E4 has this expression in terms of sum over lattice, but also there is also this another expression which I will write. Okay, this is not necessarily particularly illuminating at this stage. So once again, it has a very nice Q expansion. You can work out the Q expansion straightforwardly. That's why I write it in this way. There is another form of E4 and E2 in terms of tau, which is a little bit more, which is easier to write, but then Q expansion is complicated. So therefore, Ek belong to Mk for k greater than or equal to 4.
Starts from 1.
N starts from 1. Yes, otherwise you will get into trouble. Okay? But now let me explain to you the magic of Ramanujan, right? The point is that, suppose somebody tells you that there is a weight 12 form. How many ways can you get a weight 12 form? Right? I told you, the ring of modular forms is finitely generated. So suppose I want a weight 12 form. Let's call it F12. F12 has to be a linear combination of E6 square plus E4 cube. So that's the beauty of modular forms. So therefore, it's a two-dimensional vector space. Right? The number of weight 12 modular forms, the dimension of the weight 12 modular forms is just two-dimensional vector space. As you
Also addition different.
huh?
Ring also addition different.
On a ring, in multiplication it is not defined, but these are also functions which you can add. Right? These are functions, right? So functions, on a function you can always add.
Say finitely generated in polynomial is
Finitely generated means I can, yeah, it's a polynomial, that's what I meant, yeah. That you take arbitrary powers of these two ring elements and then you can add them with arbitrary coefficients. So it's a finite dimensional vector space generated by arbitrary powers of these two such that the weight adds up to 12 or whichever weight that you want. If you want 24, then there are more possibilities. You can get E4 square, E4 cube, sorry, E6 square, E4 cube, E6 to the 4 and E4 to the 6. These are the only.
5 or 7 or something.
So that already tells you, it's a proof. Such things don't exist. So
So I can't take a numerator by denominator. It has to be almost
holomorphic. If they are holomorphic, if you relax that condition, which is what physicists have to do, then of course there is no bound, because once you allow denominators, then you can cancel the weights, right?
Sorry, finitely generated means just by these two. That's
Huh.
finitely generated with two generators, E4 and E6.
Yes, finitely generated with real coefficients. Yeah, that's. Let me put it completely clearly that I take arbitrary powers of E4 and E6 such that the weight adds is correct, and then I can take arbitrary linear combinations of the two. Now it's clear that if we just look at the expansion of this, there is one linear combination which must be our, this is a, as I told you, it's a modular form of weight. In fact, it's a cusp modular form. It's a cusp form of weight 12. And therefore, it must be a particular linear combination of these two. But which one? All that you have to do is to make sure that this one cancels out. Right? So you know which one it is. You just write it down. E4 times E6 will have weight 10.
Yeah, that's fine. But that can have a polynomial expansion. So polynomial which one?
No. So I want weight 12.
No, not that.
Huh.
Generally, when you say polynomial, you allow the combination.
Yes. Suppose you want F10. The only F10 is E6 times. In fact, there is a unique F10, which is E6 times E4. There is nothing else.
I mean, different powers of E6 also can happen, right?
Yes. Different powers of E6. Yeah. So let's take some general example. E to the 24, right? Then it can be E6 cube, E6 square, E4 cube, plus E6 to the power 4, plus E4 to the power 6. And that was sort of, now the point is that look at these expressions, you see. They look pretty complicated. But now you have a theorem that E6 square minus E4 cube is equal to delta Q.
Proportional.
Huh?
Proportional. Because
Yeah, you have to fix the leading coefficient. There is an overall normalization. Once you fix that, is proportional to, because there is this 540 in this that we have to count. It may not be, normalization is not exactly correct. Sorry, not EK. EK is belongs to.
I see. So just E4 and E6, you don't have other E scripts, right?
There are, but they can be all expressed in terms of this. Meaning, there are Eisenstein series called, this is called Eisenstein series, by the way. And there is another definition of it, is like something like A plus M, and I forget now, say, n tau to the power k or 2k to the power k, no? Okay. So there is a general definition like that, but that definition, the Q expansion is a bit hidden. So that's why I'm giving you this definition. So this definition, however, works for any k, and those belong to mk. It's easy to check that simply because it's like a sum over lattice. They satisfy the SL to Z properties trivially. Okay. So now that sort of tells you how Ramanujan got this kinds of amazing identities. Some of them, at least. I'm not explaining. Of course, Ramanujan had many tricks in his bag, but one of the tricks was this: that you can now write an identity that this plus that is equal to that. And it looks like a amazing identity. It is an amazing identity, but underlying it is a kind of a logic that is the Q expansion and the fact that both objects are modular. You have to know that somehow.
And the fact that like the modular function is finite.
And the fact that the modular forms is the theorem that it has been finite. Now, the point is that Ramanujan might not have known all these theorems explicitly, but he knew that they were true. And therefore, some of by trial and error. And so, that's how it looked more mysterious than it was, because once you have a theorem, then it looks more, then it's a consequence of the theorem.
Is it easy to see why the modular form is finite?
There is a fairly simple proof in, I think, Sayre's book. It's not so complicated. I think you sort of integrate in the fundamental domain or something like that. I forget. And it's not a difficult proof, but it's a very non-trivial result, I think.
sorry, if I understood correctly, the lowest weight is 4.
Yes, lowest weight is 4. There is a thing called E2, which is also okay. So from this definition, it's clear that it seems to converge for any k bigger than 4. That's clear. For k equal to 2, there is a Eisenstein series, but it's not exactly modular. It's something called quasi-modular. So I will not go into that. Yeah, but here, strictly speaking, if you are dealing with holomorphic, properly defined modular forms, then k has to be greater than 4 or equal to 4. Okay. Yeah, so delta is actually this object. E4 cube minus this divided by 1728. Okay, this 1728, if you remember, this is Ramanujan's favorite 1729 number comes here. Okay. So now, let me explain why these modular forms are ubiquitous in physics. So, I mean, this is all very nice mathematics, but what is it good for in physics, right? And the reason is that two-dimensional conformal field theories two-dimensional conformal theory is a huge field of physical problems. In many statistical systems, people come across it. Lots of critical points are described by two-dimensional conformal field theories. They also appear as string world sheet. The string theory moving in some background, the world sheet is a two-dimensional conformal field theory. They can also be the low-lying description of some complicated brain configuration, which again looks like a two-dimensional conformal field theory. So, two-dimensional conformal field theories, there is a very, and thanks to the work of Belavin, Polyakov and Zamolodchikov, we understand two-dimensional conformal field theories kind of abstractly. So the two-dimensional conformal field theories are very interesting because they give a definition of, a non-perturbative definition of quantum field theory. So this was the kind of a point of view that was pioneered by Polyakov, that, and then really put substance into this in this BPZ paper, that normally we think of a path integral and some action. Polyakov sort of said that, okay, you don't, in terms of a stress tensor, operator product expansion, list of operators, he just gave an abstract definition of a two-dimensional conformal field theory, and some bootstrap equations have to be solved. And then you don't even need an action, there is no path integral. But still, you can learn a lot about that theory. And these methods now have been generalized to higher dimensions. So this bootstrap, you might have heard, some of you, techniques have been now applied in 3 dimensions and 4 dimensions. But in 2 dimensions, because the conformal group is infinite dimensional, you have a lot more control and you can really solve everything. So they are kind of very interesting from various points of views. And then it is easy to understand that if you have a partition function, or one loop partition, a partition function, is modular invariant. If it is diffeomorphism invariant. Why is that? Because, see, if you write down some action like a scalar, right? Let's consider two-dimensional action. Euclidean partition function. So these are all 2D Euclidean, actually I'm talking about for now. Then a partition function is like on a torus, how should I explain this? So this is your action. Okay, so you're trying to do this path integral over 5 fields defined on this torus with some tau parameter. And basically using two-dimensional diffeomorphism invariance, you can bring this into just some scale factor. But if it is conformal, even the scale factor drops out. And the whole thing is basically invariant under, and conformal, the tau going to A tau plus B times C tau plus D R can be thought of as global diffeomorphisms or large diffeomorphisms or global diffeomorphisms. So what is a diffeomorphism? That if I deform right of a manifold, if I just make a small coordinate transformation, then that's a local diffeomorphism. But here, since tau is obtained by just making an identification of a lattice, if I take tau, if I make this identification, I still get back the same torus up to a Weil transformation. But if this theory is conformal, then it's Weil invariant, so the overall Weil factor doesn't matter. So another way to say that is that, okay, let me write it differently. The metric, see here the metric is flat. Okay, here the metric is flat, dz plus dz dz bar, right? And z is identified with z plus tau, right? This is what I mean by, let me write it slightly differently. You can also write it as ds square is equal to, so it's really dx square plus dy square. But you can also write it as, by making an appropriate transformation, you can write it as x, or let me call it sigma, okay, x1 plus x2 square. I can write it as d sigma 1 plus tau d sigma 2 square. The metric of a torus, I mean another way to say that is that you normally think of a torus as something in flat space-time, right? In flat plane with these kind of identifications. But you can make a coordinate transformation to sort of straighten this, so that the identification is, so here that identification is a bit complicated, right? Z goes to Z plus tau. But you can make a transformation such that you have sigma 1 is identified with sigma 1 plus 1 and sigma 2 is identified with sigma 2 plus 1. So the identification, yeah, so what I'm saying is that you can either have a simple metric and a complicated identification, namely slightly tilted identification, or you can do a coordinate transformation and straighten it. And in these new coordinates, the identification is simple, but the metric is a little bit more complicated, which looks like this. There is a tau here, it's not flat metric. And now it's easy to see that when you make a transformation like that, this metric basically picks up an overall phase, sorry, overall scale factor like c tau plus d to some power square or something like that. And if your action is Weil invariant, it doesn't matter. And therefore, every conformal field theory has modular symmetry. Is that clear? So basically, modular symmetry is a consequence of conformal. And therefore, if you have a diffeomorphism and Weil invariant theory, then it has to be modular invariant. Because modular symmetry is a combination of global diffeomorphism and Weil rescaling. If your theory is invariant under that symmetry, if your action is invariant under that symmetry. See, this action is diffeomorphism invariant. Moreover, this action is also Weil invariant, because if I rescale the metric G, square root of G and G mu nu cancel, right? If I scale the metric G going to e to the 2 omega G mu nu, then only in 2 dimensions, G upper mu nu goes to e to the minus 2 omega G mu nu, and square root of G goes to e to the plus 2 omega G mu, square root of G. So these two factors cancel, and this action is while invariant. And it's a consequence of that while invariance and diffeomorphism invariance that modular symmetry is so ubiquitous. So whenever you have a conformal field theory, you'll always find modular symmetry. Huh? No, so this is a theory. If I take a free scalar field, this is a theory with a Lagrangian description. Yes, yes. In that case, you put modular invariance as an additional constraint, exactly. Following the intuition that in theories that we do have Lagrangian description, and you insist on global diffeomorphism and while invariance, then modular symmetry is a symmetry as an additional condition. Yeah, you need not, but then it would result from some action. It would correspond to some action which is not diffeomorphism invariant or not while invariant, one of the two. Yeah, or may not have Lagrangian. Okay. Huh? Sorry?
It's a holomorphic. It is already diffeomorphic.
No, so we are talking about two different things. The function was holomorphic. I'm talking about now the partition function. So the partition function is actually not holomorphic. No, it can depend on tau bar. So let's take an example of a free scalar field, right? A free scalar field. Let's just do. Right? If you just quantize, for example, a free scalar field in flat space. The partition function on a torus. This partition function can be easily worked out actually. It's easier to think about this as a trace, because as you know, any path integral, you can think of this as time and think of this as a trace. So z of tau bar is actually trace. So suppose you had a, so this is identified, right? So it's like a string going up and you are identifying, propagating for say time 2 pi tau 2. Then how will you write down the trace? You will write it down e to the minus 2 pi tau 2 times the Hamiltonian in 2 dimensions. But the Hamiltonian is the Virasoro generator is L0 plus L0 bar. And if you want to sort of move in this direction, you have to sort of, what you're doing is that you're not identifying the string directly, but you're sort of identifying with a twist. You're translating along the string, but translation along the string is performed by the momentum operator. So it's like root 2 pi I tau 1, but momentum operator is L0 minus L0 bar. And so this becomes trace of q to the L0, q bar to the L0 bar. Okay, so the path integral, you can either do the path integral directly, you can also do it as a trace. And when you do it as a trace, if you remember, I'm just trying to remind you, this you just give the eta functions and you get product of 1 minus q to the n, q to the 1 upon 24 absolute value square divided by tau 2. This comes from the 0 mode integral. So, and this is modular invariant, you can check. Because this transforms in a certain way, this tau 2 transforms in a certain way, and it says that it's modular invariant.
I see. These are just 2 sheets. There's a cut. Yeah, on each sheet is almost.
No, it's a holomorphic and anti-holomorphic combined, right? It's an absolute value square.
Yeah, but There are two sheets.
There are no sheets, right? This is just a holomorphic function.
On each of them is holomorphic.
Yes.
Holomorphic or integral.
Yes. It's a basically taking a function and it's a complex conjugate and multiplying the two. Right? It's like absolute value of a holomorphic function.
Yeah.
So it's true that you can think of it as a holomorphic function on the z plane and another holomorphic function on the z bar plane.
So two are combined.
Yes.
Like a cut,
Okay.
not cut.
Yes. Okay. So this sort of explains why we are interested in these kinds of functions. Okay. Where does string theory come into and black holes come into the story? So by the way, how did we do this calculation? How did we get this product? If you remember, if you look at the Hamiltonian of a free boson, right? A free boson will have e to the minus I n tau plus sigma a n plus e to the minus I n tau minus sigma a n tilde, some expansion like that. Plus there is a zero mode phi 0 plus a momentum pi tau like that. Okay. So if you just do if you remember your first course in string theory or something like that. And these are oscillators. You see, this is exactly the kind of oscillators I was talking about. And the Hamiltonian L0 is basically n times a n dagger a n plus pi square upon 2 or something like that. L0 bar is n times a n tilde dagger a n tilde. So these are basically left moving oscillations and the right moving oscillations on the string, which are labeled by an integer. And therefore, it is natural that you get this 1 minus q to the n coming from that integral. And then this pi square integral is like a momentum integral of a free particle. And that gives you the tau 2 dependence. Okay. And now you could also do just purely the holomorphic side. In some cases, you do this purely holomorphic side. The purely holomorphic side gives you eta this pi 1 upon q. So the point is that if you now have to the power 24, and this q to the 24 becomes multiplied by to the power 24 becomes q. And this was our friend from yesterday. Incidentally, this 24 is also important, as you know. It just comes from 0 point energy of this, right? The 0 point energy of this, of an oscillator, is h bar omega over 2. So let me explain this 1 upon 24, right? Where did we get this q to the 1 upon 24? Because the Hamiltonian actually is n a n dagger a n plus half sum over n. And Ramanujan correctly realized that half sum over n going from 1 to infinity is actually not infinite, but it's 1 upon 24. Minus 1 upon 24, sorry.
1 upon 12.
I mean, this is 1 upon 12, and with a factor of half, it's 1 upon 20. Now, this is not actually, by the way, so Euler also had done similar things. The point is that it's not something, sometimes this is stated as, okay, these physicists do some kind of crazy tricks on this. There is absolutely no crazy trick here. So what you're doing is that it's completely consistent with our understanding of renormalization theory, right? When you define a path integral, you're allowed to add local counter terms. You're supposed to add local counter terms because you don't know. There is a local counter term that you can add in any two-dimensional theory, which is of the, suppose you put some cutoff, then it is, the local counter term is of this form, d2x times lambda. And what you find is that when you do this integral, you regulate it. You can remove the divergent piece by adding a local counter term. But the subleading term, which is not divergent, is universal, and it is not affected by the local counter term. So that is why it's not just some magic, you know. Of course, you can do a zeta function regularization and you will get this, but there is a more physical way of understanding why this 1 upon sum over n is minus 1 upon 24.
Did Ramanujan actually know this?
Ramanujan used zeta function, I think. And if you do zeta function regularization, but I think Euler knew this. I mean, Euler, I think, did something like this, that e to the minus n epsilon you can do. Right, you regulate it like that. And then you throw away a term which is 1 upon epsilon square or something like that.
So what are lines?
Minus 1 upon 12. No, he was thinking like a physicist that, okay, I can give meaning to this term up to counter terms. You know, I mean, up to some divergent piece. I mean, what I'm saying is that he understood that this species does not depend on how I regulate it. So you can do zeta function regularization, epsilon regulator. You'll always get, this term is not affected by it. So it's kind of universal.
The formulation we can subtract also some finite part. So, the description contains that some kind of choice. We subtract 1 over epsilon plus something.
Yeah, the thing is that if you actually, if you substitute the, if you put in the length, it's actually 1 upon length. You see, this is energy, right? So it should have dimensions of 1 upon length. So you are not allowed to add a local counter term that depends on L. It's not a local then, right? If it depends on how big is your universe, then that counter term is not local. Yeah, if you
Make some extra thing. Subtraction always not enough. Something else has to be.
yes, and the local, I mean, the point is that if you take the string to be of the size 2 pi, then it's not clear. But if you make it 2 pi L, then by dimensional analysis, energy has to be proportional to 1 upon L. And this term you cannot subtract. I mean, you could subtract it, but it's not.
Also a dimension.
Huh?
Also a dimension.
Yeah, but lambda is like a cosmological constant. It's local, right? You don't want the cosmological constant to depend on the size of the universe, right? Another way to say that is that.
It's lambda times the area. The area is the size.
But it's not 1 upon L. Meaning, yeah, what you're saying is right, but if you try to do it, you will find out that you cannot actually remove this piece by a local counter term. Okay, very good.
Just started one more question. So like this way of doing you always get as 1 over q over r. So this in your classification is weakly holomorphic.
This is weakly holomorphic.
So the question is there any way that I can construct a 1 plus 1 field theory which will give me the holomorphic one?
Yes, so for example, fermions always come on top. Yes, so fermions, so this is actually, if I did a fermionic partition function, see, why did I get this in the numerator? If I do a bosonic partition function, it goes like 1 plus q to the n plus q to the 2n, right? Because for a harmonic oscillator of frequency, I mean, let's say omega, right? For a harmonic oscillator of frequency omega, right? I have states which are like 1, 2, 3 and so on, right? An infinite set of states, such that the energy is n times h bar omega plus half. But for a fermion, and this then becomes 1 upon 1 minus q to the omega. But for a fermion, it just stops here because of the Pauli exclusion principle.
So this is like so this means like it can give me modular forms of any weight.
Yes. So depending on the content of the theory, if you have a purely fermionic, I mean, it is possible to get modular forms of different.
So from this point of view, is it possible to understand why I cannot have a modular form of weight 5 or some such arbitrary thing? I mean, because previously when the center can be finitely generated, I can get only those modular forms with whatever I can construct out of D4 and D6.
You see,
For odd weight, actually, it seems
So the question is, can I understand that result from this kind of?
no, the thing is that when you do a path integral, you are not necessarily in the world of holomorphic things, right? You get absolute value square. And then none of these theorems really apply. Right, like the eta function itself. See, eta function itself is a modular form of weight 1 in some sense. right? Because it's the, sorry, weight half, because it's the 24th root of a weight 12 form. But it does not exist as a holomorphic, I mean, it's not classified in the holomorphic thing of the SL2 set, okay? Then you can extend your definition and so the fact that we got eta here already shows that in physics problems you can get more general things. Then okay, I'm going a bit slow, but it's okay. Okay, so sorry, where is the eraser? Here. Okay, I think what I will do now is so basically I have defined modular forms. Then there is another object called Jacobi forms. Then there is a third object called meromorphic Jacobi forms. And then the fourth object is going to be mock Jacobi form, okay? And this is where it relates to Ramanujan's work on mock modular forms. And the connection between these two was basically the subject of the collaboration with Zagier, myself, Samir Murthy and Zagier. And what we showed was we proved a kind of a decomposition theorem. That related meromorphic Jacobi forms to mock Jacobi forms, and it turns out that it has a very nice interpretation in multi-centered black holes, and which I had mentioned yesterday's colloquium, but I will explain that. But Jacobi form is there is a very, so this is now completely understood, right? Now we understand it completely, right? It's a finitely generated ring, end of story, right? You don't need to know anything more. Similarly, Jacobi forms is also completely understood. It's a finitely generated thing. I will explain in a moment. So there are basically two basic Jacobi forms, and you can write down every other Jacobi form as an appropriate combination of those two. So just like here, once you understood E4 and these two objects are more complicated, and so let me first describe what this Jacobi form is. So this was a function just of tau. Now in quite a number of physics applications, it can also be a function of tau and z. So if you want to just keep a geometric picture in mind, see if you have a torus, a two-dimensional torus with tau, and the z can be a coordinate on the torus. So in general, you can imagine functions which are functions of z and tau. And a simple example that you know are the theta functions. Many of you have encountered theta functions. Theta function is an example of a Jacobi form. I mean, in fact, Jacobi theta function, that's why they're called Jacobi forms. It's a kind of a generalization of Jacobi theta functions to make it into a definition. So this was done by Eichler and Zagier. This is a nice book by them. Once again, they appear very naturally in many physics problems, where you are computing instead of, so here we see, suppose you are computing trace q to the L naught, that gave you modular forms. In some cases, in supersymmetric quantum mechanics, you can calculate trace minus 1 to the f and some y to some j q to the L naught. You know, see, it's some other trace where y is equal to e to the 2 pi I z and q is equal to e to the 2 pi I tau. So another way to think about it is that if you have a 1 plus 1 dimensional conformal field theory or 2-dimensional conformal field theory, if you just computed the canonical partition function, right? If you computed the canonical partition function, then it would be like a trace of e to the minus 2 pi beta. I'm just putting the 2 pi just to make things simple, but I mean, normally you write it beta times Hamiltonian, right? Let's write it 2 pi beta. This is canonical, right? Because you have temperature. But now suppose you have some other conserved charge J in the theory, then you can do a grand canonical ensemble with some chemical potential for that. So in general you can compute e to the minus 2 pi mu times some J. So therefore modular forms occur naturally when you are dealing with, in some sense, the canonical partition function of a conformal field theory, and sometimes it's holomorphic just for the left movers. And Jacobi forms occur naturally if you are in problems where you are interested in some kind of a grand canonical ensemble, where in addition to the Hamiltonian or the L0, you also have some charge J which is conserved and which you want to, and particularly in supersymmetric theories that J is.
So if I have a grand canonical ensemble not only with one more thing but with some 3 or 4 more conserved quantities, then I should be having a.
Yeah, so there are actually generalizations where you make Z into a vector. You can do that.
So therefore in that case the Z vector is not really like a point.
Yeah. In that case it is a different interpretation. No, these are higher. No, it's not higher genus because tau is just tau. Yeah. I mean, okay, so remove this from your picture. I mean, okay, you have Z and Z hat. Okay. Yeah, the main point is that if you want to think about it from a physics point of view, just think you have a 2D CFT and you want to calculate things like trace Q to the L0, then you will naturally land up with modular forms. If you compute trace Q to the L0 times Y to the J, and typically J in supersymmetric theories, supersymmetric conformal field theories, J is usually some R symmetry, U1 R symmetry. And of course there are generalizations when you can have more than one U1s and things like that. But the best understood is actually with a single variable, Jacobi forms, because there again there is a classification theorem, meaning a proof that any Jacobi form can be generated. So let me give you some examples of. So here I gave you examples, right? I mean, not only examples, I gave you proof. I mean, not a proof, I stated a theorem. Yes. Yes, exactly. Yes. So Jacobi form, a modular form, is specified by its weight. The Jacobi form is specified, so basically, let me write it as like that, Fk of tau. So this is called weight. A Jacobi form is specified by a weight and an index, and it's a function of two variables. So this is weight and this is index. And the basic idea is very simple. The basic idea is the following. I mean, what is the importance of theta functions? Why did theta functions enter into mathematics? Is that you have a doubly periodic function, right? So it's kind of what is known as an elliptic property. The elliptic functions have the property that if they are functions of z, and if you take z going to z plus m plus n tau, the function is invariant or it comes back up to a phase. Okay? So there are basically two interesting transformations. One is, I mean, if you think of it as a torus, right? If I translate this z by m plus n tau, if it's a doubly periodic function, then you expect this to be a symmetry. And then there is a modular symmetry. So modular forms are symmetric under the modular group. Jacobi forms are elliptic in the z variable and modular in the tau variable. So that's one way to understand. Think of them.
So the same n.
Yeah, let me call it alpha and beta, where alpha and beta are integers. So let me give you a couple of two examples which are in fact very important. And so there is a whole story here for Jacobi forms. Okay, I'll come to that. Yes?
They will also have an M index.
They will have an M index. So let me first state. So there is, just like you have E4 and E6, I will give you an example, but there is phi 0, 1 and phi minus 2, 1 are two Jacobi forms. I will give you, I can write down for you a very explicit expression. This is theta 1 square z tau divided by eta to the 6 tau. Okay, so if you remember, there are these four Jacobi theta functions, theta 1, theta 2, theta 3, theta 4. Okay, if you remember.
Are the weights and indices integers?
Yes. And this is equal to half theta 2 square z tau divided by theta 2 square tau, 0 tau, plus same for theta 3 square z tau, theta 3 square 0 tau, plus theta 4 square z tau, theta 4 square 0 tau. And let me just remind you, for example, theta 1 square, if you don't remember, right? Theta 1 square z tau, these are very explicit expressions, right? It's like something like minus 2 sine pi z product, q to the 1/8 or something like that. Product 1 minus q to the n, 1 minus q to the n y, 1 minus q to the n y inverse. That's a theta function, okay? That's a completely explicit formula, whereas eta of tau is q to the 124 product 1 minus q to the n. Sorry, theta 1. Theta 1 is that, and theta 2, theta 4 can be obtained from this by just shifting z, by some half shifts of z. Half. And y, yeah, q is equal to e to the 2 pi I tau, and y is equal to e to the 2 pi I z. And once again, the theorem of Eichler and Zagier is that any Jacobi form with appropriate holomorphic properties, which can be generated by multiplying this, but this time the coefficients can be modular forms. So for example, you want index, suppose you want index 2 and weight 4. Right, what can you do? You can take phi 0, 1, you want index, this is index, okay? Square, but that doesn't have weight. So you can multiply this by E4, but then that will give you the weight. That depends only on tau. This depends on z and tau. Plus, you could take this also, square, and multiply this by E6 maybe. Okay, I got it wrong. Maybe it will work.
We can put something of weight 6.
Okay, this is not a good example. I'm just trying to think of a better example. Maybe let's take weight 6.
Actually, right, that's for whatever expression you want.
Yeah. 5 to 1 minus 2 1.
Yeah, but then this will have weight 4, and then you can take E4 square maybe. Yeah, that will work. So once again, the ring of Jacobi,
5 minus 2. And there's also cross term.
and there could be cross terms also. Yes.
So what is this 5 minus 1?
The weight is minus 2 here. Because you remember this has weight, okay, so theta 1 has roughly like weight half. So theta 1 square has weight 1, eta has like weight half, so this has weight 3, and 1 minus 3 is minus 2. And you can index of theta 1 is 1. So theta is roughly speaking weight, I mean it's not strictly correct, but I mean index half. Index 1. Index half for theta 1. Okay, yeah.
So DCs themselves cannot be expressed as in terms of Jacobi thing for
No, because they are functions only of tau, right? Whereas Jacobis are functions of z and tau.
special value of z. Can the E for DCs get upon the Jacobi form?
Yeah, because they can be, because actually eta function, eta of tau, for example, eta of tau is a theta prime z of tau evaluated at z is equal to 0. So there can be ways to.
Index has to be always non-zero.
Yes.
But index 0 is modular form.
Huh.
I understand, but how do I see that as a special case of this theorem?
Yeah. So this theorem, okay, I'll have to now explain. I mean, there is more, if I really want to do a good job of it, there is more stuff to it. But okay.
So the modular forms can be seen as a special case of Jacobi.
No. Because modular forms are functions of a single variable, whereas Jacobi forms are functions of two variables.
I should be able to switch it off.
Yeah, if you set that j equal to 0,
Yeah.
there may be, yeah.
You can
No,
do it for 501 and 5 minus 2.
no, if you put this equal to 0, z equal to 0, this just becomes 12. It's a constant.
It's a number.
It's a number.
Other one is 0.
So, but the statement is that Jacobi forms are also finitely generated. I mean, let me make it let me make a very practical statement. Right? The practical statement is that any Jacobi form you can obtain by taking appropriate powers of phi 0 and phi minus 2 and allowing yourself multiplication by modular forms such that the weight adds up. That's the meaning of saying that it's a ring finitely generated with coefficients in modular, whose coefficients are modular forms. Whereas earlier the coefficients were real numbers, right? Whereas here the coefficients themselves can be modular forms because they depend only on tau.
The coefficient may be arbitrary power and coefficient linear combination.
Yes. Yeah. It can be, you can get e4 to the power 6 and whatever. Yeah. Right. But once again, it's a theorem, so it's completely done and dealt with, and nothing to be worried about. And it's very natural actually. In these two objects actually are very closely related. So there is a very beautiful connection of, so quantum black holes relate to two different branches of mathematics. One is of course modular forms, but the other is enumerative geometry, or and this is something I cannot explain, but it's related to this deep brain physics and so on. But basically there is a combinatorics problem that I came across. That combinatorics problem arises in string theory by studying some brain systems. For example, here, this is the elliptic genus of, this is related to there is something called the elliptic genus, which I will define in a moment, of K3 and T4. So if you just take a conformal field theory, super conformal field theory, whose target space is K3, and you try to compute this elliptic genus, which you can compute actually. And elliptic, what is an elliptic genus? Elliptic genus is some very simple thing like that. It's trace minus 1 to the f, q to the L0, y to the j in the Ramond sector. Okay, I mean, you can also define it in an S sector, but okay, there's one definition and that gives you this object. So basically, you just look at the Neveu-Schwarz-Ramond string whose target space is K3, it's just some sigma model, or whose target space is T4. T4 is very simple. So this T4 is extremely simple, right? There are 4 free bosons and 4 free fermions. Okay, so it's kind of easy to see. You see, if you look at it, it's going to have pi, roughly speaking, and you immediately recognize these are 4 bosons, right? And these are 4 fermions. And the fermions are charged under the J symmetry. And that's why you get Y dependence only on the top and not on the bottom. So basically, if you were just computing a partition function of fermions, 4 fermions and 4 bosons, fermions will, and this minus sign relates to the fact that you're computing trace minus 1 to the F, so there is a minus sign. And Ramond sector means that they are integer moded. If they were Neveu-Schwarz sector, then they would be half integer modings. So basically, you can completely understand this calculation, this object, by a very simple physical calculation on T4. If you just compute, just take 4 free bosons, 4 free fermions, right? Simplest possible conformal field theory, you can imagine. It has an underlying, and there is a rotational symmetry. If you just rotate the fermions in pairs, that is the symmetry that is J, that is generated by J. So give for that symmetry, you just now write down the partition function with using oscillators, free oscillators. And you will clearly get something like this, right? So it's not something very exotic mathematics. I mean, it's exotic mathematics at the face of it, but it comes across in a very natural way. For K3, this computation is a little bit complicated, but if you think of K3 as T4 mod Z2 orbifold, okay, then it's a relatively, again, it becomes like a free oscillator calculation, and you can calculate it very explicitly. So, the 2 very natural objects that come in the Eichler-Zagier theorem are also very natural from the physics point of view, and they come very naturally in the K3 and T4 superconformal field theory partition functions. Okay. Now, how does it relate to enumerative geometry and black holes, right? What is this connection? So the point is that, as I told you, a black hole was represented the more general picture in string theory, that which I have simplified yesterday, was you have, suppose you have some 10-dimensional theory. You write it as a 4-dimensional theory cross some 6-dimensional manifold, which typically is some Calabi-Yau manifold, 6-dimensional, I mean, or complex 3-dimensional Calabi-Yau threefold. Or this can be K3 cross T2, for example, which can, some of the examples are T6 or K3 cross T2 or more general Calabi-Yau manifolds. Then the picture is that you have a black hole in 4 dimensions, but it has some internal structure. Inside this Calabi-Yau manifold, inside this compact manifold, it is some very complicated brane configuration. In the simplest example that I consider, it was just a string wrapping one of the circles in the heterotic frame. It was a string wrapping many times and oscillating in 24 dimensions, right? But more generally, it can be a more complicated brane configuration. Something doing, so basically this is your R 1, 3. But this looks, if you look at it in the M6, your M6 is some complicated manifold, you know, with some cohomology and some topology. And it can be some brane wrapping one of the cycles, some other brane wrapping some other cycles, and you're trying to find the number of bound states of such branes. And that problem is basically a problem in enumerative geometry, that given us a manifold, given some complicated cycles, okay, how do you count the number of ways? That is, so to give you a simple example, this, if you consider just K3, let's say, so you just compactify to 6 dimensions. Now the K3, in the case of K3, you can take K3 is a 4-dimensional manifold. You can wrap a 4 brane on the K3, and then you can have some number of 0 branes. Okay, so K3, these are called D4 branes and D0 branes. and you want to know how many bound states are there. And this problem actually leads exactly because of the fact that the Euler character of K3 is 24. The counting problem, so this is a very complicated problem, right? D4 brane is some gauge theory living on the entire K3 because D4 brane has a gauge theory living on it. And D0 brane can be represented by instantons in that. So basically this reduces to a problem of find the Euler character of the instanton modular space. Of, let's say, n instantons on a super Yang-Mills theory that is living on this D4 brane, but the D4 brane is wrapping all of K3. So n instantons correspond to n D0 branes. So the Euler character gives you the number of bound states of a single D0 brane with single D4 brane with n D0 branes. And this problem is exactly the problem that we had constructed. Okay, the coefficients of this exactly give you this. And it's not an accident. This 24 is the Euler character of 24. And roughly speaking, the idea is that Euler character, if you remember, is the number of even cohomology, the Betti number of even cohomology, and is the Betti number of odd cohomology. But K3, if you remember, K3 actually has only even. So it has a 0 cycle, no 1 cycle, it has a 2 cycle, no 3 cycles, and only a 4 cycle. And roughly speaking, even cohomology corresponds to bosons, and odd cohomology corresponds to fermions. For the simple reason that their partition function, one comes in the numerator, one comes in the denominator. So if you expand it, one comes with a positive sign, the other comes with a negative sign. So we want to sort of incorporate this minus sign. So basically, if you have some manifold and you want to calculate this Euler character by doing some kind of a conformal field theory calculation I was explaining here, then even an odd cohomology corresponds to bosons and fermions. And here in this case, because they have only bosons, you get only thing in the denominator, nothing in the... And the 24 is related to the fact that the Euler character... So, but
where is the number of instantons coming?
This you write it as Pn q to the n. And that Pn is the Euler character. And this was actually one of the first pieces of evidence for duality. See, this D4 D0 system in the type 1 string is related to the heterotic string. So it's a highly non-trivial fact that the heterotic string oscillating in 24 transverse directions and the 24 is related to the Leach lattice and so on, which is what the heterotic string had done many years ago. But after duality, we understood that that is actually related to properties of K3 in a very non-trivial way. So this actually, I mean, Euler character itself is an index. You can write it as an index. Euler character you can think of as a Witten index of the corresponding supersymmetric quantum mechanics. And that index is exactly Pn. Is this, is related by this.
So let's go again. So the D4 brane wrapping K3 is like the heterotic string. And the normal...
Yeah, no, so actually the correct statement is that NS5 brane of the type 2 becomes a heterotic string. So you have to do some T...
N theory or something.
you do a T duality on one circle so that you get a NS5 brane. So then you have a... Yeah, so there is a bit of... Yeah, bit of duality is involved, but basic point is that an NS5 brane wrapping K3 is the heterotic string. So the heterotic string wrapping some circle is the same as an NS5 brane wrapping that circle and this. Then you do some dualities and you can map it to a D4 D0 system.
So what is the independent check of this D0 for being included?
Yeah, so this was one of the initial evidence. Actually, this was a computation by Witten and Waffa, and they were very surprised by this because it looked like these perturbative states that Harvey and I had talked about, and they said, okay, it looks like those states, and they made some conjecture, but they didn't really push it forward. But now that we know that, okay, so this is related to type 2A heterotic duality. So it was actually not, they did not really understand it. I mean, this looks like a miraculous fact, right? Why does it happen like that? But now, since then, there has been much more evidence for this duality. And from that duality, of course, this duality is never proven because dualities are not proven. None of the dualities can be really proven. But there is, I mean, so the point is that this fact can be very naturally explained from that point of view. Also, the fact that there is a conformal symmetry here looks a bit strange from a priori. Why does it have modular properties, right? This is not obvious. But from duality it's obvious because in the dual frame, this corresponds to a string, so there is a conformal symmetry. So a lot of these things which look very mysterious to mathematicians are suddenly completely obvious from a duality perspective. But I mean, that's why I think this is an exciting, I mean, it's clearly something that will develop slowly over the years, and eventually people will really understand it. I mean, there will be one day there will be a proof of duality. I don't know. Huh?
The dualities will lose their utility.
Yes, once there is a proof, then there. Okay, I think I should stop here because I didn't get down to mock modular forms. But I think this is okay. We can think about tomorrow, but I can't see. Okay.